The first talk is given by Surendra Ghentiyala from UCSB. And he's going to talk about how to estimate information leakage using bounded model checking.
Thank you. I'll be talking to you, as she said, about approximate model counting and obtaining information leakage. This was work done at UC Santa Barbara with Seemanta Saha, Shihua, Tevfik Bultan, and Lucas Bang from Harvey Mudd. I'm currently at Cornell, advised by Noah Stevens-Davidovitz. What's the problem we're trying to address? Programs, regardless of functional weaknesses or user error, leak information. What do we mean by that? Well, a program has two kinds of inputs. It has a public input, which is known to everyone, and a secret input, which we want to keep hidden from an adversary, like a cryptographic key. It takes these inputs, does some computation with it, and then outputs something through the main channel, the channel through which we expect information. However, many programs also output information inadvertently through side channels, like execution time or memory usage. We say that a program leaks information when you can deduce something about the secret input by looking at the output, either through the main or side channel. Luckily, there's an existing framework to address these types of issues. You would take this framework, put a program into it, and it would tell you that your program leaks something like 1.2 bits of information. However, these current methods have their limitations. In particular, the symbolic execution stage might fail, and the model counting phase might fail as well or return inexact model counts. We'll get into what this means in a second. What our tool allows you to do is to give bounds on information leakage when these two steps are inexact. If you come away remembering nothing else from this talk, remember this, that when these two steps fail, we're still able to provide bounds on information leakage. Before we see how these steps fail and how we can remedy that, let's take a look at an example and how it's supposed to function ideally. Here's a program which leaks information. It takes in two strings, a string H, the high input, which we want to keep secret, and the string L, the low input, which we are fine with being public. It compares the strings and then returns which one is greater in lexicographic order. The reason it leaks information is due to early termination. It compares the strings one by one, and then as soon as it sees that there's a mismatch, it returns which one is greater in the lexicographic order. So an adversary can tell how much of the string matched by observing how long the program took. The longer it took, the more the two strings matched. We take this program and we feed it into a symbolic execution engine to get path constraints. These are the path constraints right here. We fixed the low input to be a specific string, in this case info, I-N-F-O, and let's look at what the path constraints represent. So path constraint 1 represents when the high input, the first character is not I, and you make only one iteration through the loop, and you say that H is less than L. This corresponds to one iteration in the loop here. The second input corresponds to one iteration in the loop, but saying that H is greater than L. The third iteration corresponds to two iterations in the loop, and so on. Each path here corresponds to exactly one constraint. Then we group these path constraints in terms of how long each one of these paths through the programs take. So we see paths 1 and 2 both take 57 instructions, so to an adversary, they're indistinguishable. This is not quite true, and we can get into that in a little bit. But paths 3 and 4 take 83 instructions, and we say that they're the same. We take these paths and we feed them to a model counter, which tells us the number of satisfying assignments to these constraints. So constraints 3 and 4 have something like 16 million satisfying assignments. Then we divided the model counts by the domain size to get the probability that on a random H, this path is taken. So we see that paths 3 and 4 are taken with probability 0.3% on a random H. We take these path probabilities and feed it into the Shannon entropy formula to get how much information this program leaks. Intuitively, the more uniform the distribution of runtimes is, the more information the program leaks. And if you only have one runtime, which occurs 100% of the time, that leaks no information, and that has Shannon entropy 0. There's more information theoretic ways to think about it, but that's the intuition. So where exactly does this fail? The first step where this fails is the symbolic execution phase. Symbolic execution engines have gotten quite good, but they're not perfect. There's always the issue of path explosion. The number of paths grows very quickly with the size of the program. And many of the satisfiability problems we need to solve to explore a specific path might not be solvable in time by a symbolic execution engine. Our method provides bounds on information leakage when this is not possible. On the right, you'll see a graph which tells you that as the percent of the input space unexplored grows, the bounds on entropy grow as well. The red is the upper bound and the blue is the lower bound. The second issue is that exact model counting is often impossible. It's generally limited to integer linear arithmetic constraints and regular string constraints, as well as a couple others. But we can relax this and use an approximate model counter, which instead of giving us an exact model count of 300 would tell you that the model count is somewhere between 200 and 400. We then propagate this uncertainty into the bound on information leakage. On the right, again, you see that as the approximation tolerance, how large the bounds that the model counter gives grows, the entropy bounds that we give grow looser as well. So let's get into how exactly we bound information leakage using these methods. Here we have the Shannon entropy formula. The probability, the Shannon entropy is equal to the sum over the probabilities of the probability of observing a certain runtime times log base 2 of 1 over the probability of observing that runtime. For us, since we're dealing with model counts, the probability of observing a certain runtime is the model count divided by the domain size. And when that model count is uncertain and we want an upper bound, we can simply maximize over all possible instantiations of the model counts. We maximize the Shannon entropy, where each count is between the lower and upper bound given by the model counter, and the sum of the model counts is equal to the domain size. To get a lower bound, we do the same thing, except we minimize. Let's try to gain some intuition for how this works exactly. Here is an example instance of the maximization problem. Let's say that the model counter has told us that all the counts are between 5 and 15, and the sum of the counts is equal to 60. The Shannon entropy is then minimized when all of the counts equal 6, the uniform distribution. This is a very simple example. Let's see what it looks like when the model counter doesn't give us such simple bounds. Here, the bounds are a little bit more erratic, but we see that the Shannon entropy is also maximized when the counts are as balanced as possible. For the minimization problem, we have the same instance where all the bounds are between 5 and 15, and the sum of the counts is 60. And the Shannon entropy is then minimized when the distribution is as unbalanced as possible. And again, with a more complicated example, we have the same thing. The distribution is as unbalanced as possible within the constraints that we have. So let's see if we can leverage this insight to create algorithms to upper and lower bound Shannon entropy. Shannon entropy is a concave function with respect to event probabilities. Therefore, there's only one local maximum. So we can simply use the hill climbing algorithm to arrive at that local maximum. As for lower bounding, it's a little bit more complicated, but we see that the domain that we're optimizing over is a convex polyhedron. The minimum of a concave function over a convex polyhedron occurs at the extremal values, and that's exactly what we saw. So we simply optimize over all the extremal values. How do these two things fit together when you have both unexplored paths and approximate counts? Well, the optimization problem grows more complicated, and I could talk about this for quite a long time. It's very interesting, but all you need to know is that it reduces to the instance I've already covered where you only have approximate counts with an O of 1 overhead for the upper bound and an O of n overhead for the lower bound. These are not actually the algorithms we use in practice, but we use modified versions of these in the paper, and we can get n log n for the upper bound and n times 2 to the n for the lower bound. The experimental setup, it's not too interesting. We compute exact leakage, and then we relax the constraints to get upper and lower bounds. So here we see the channel capacity, which acts as an upper bound for Shannon entropy, and then we see the exact bound in red, and then we see the bounds that our algorithms gives in gray. And as you increase the approximation tolerance, the bounds grow looser. This is the bounds computed using an actual model counter, and you can see that we still do better than channel capacity using an approximate model counter. In conclusion, the methods used currently are inflexible and they're brittle. We managed to provide bounds when some of the crucial steps break. These are probabilistically sound bounds, and the experimental results demonstrate the feasibility of such an approach. Thank you.
Questions? If you have a question, line up in the queue. Go ahead.
Hey, Marco Guarnieri in the software. Very nice talk.
Thank you.
Okay, one thing I was really wondering about is, in the information flow, in the quantifying information flow community, people explored a lot of different entropy-based metrics, like, mean entropy, guessing entropy, Iranian entropy, and I was wondering, can some of this be applied to your setting, or what do you need to change?
That's a fantastic question. I was hoping somebody would ask it. Thank you.
Hey.
So you are correct. There is still some debate in the literature about what is the correct measure of information leakage, and one of my collaborators has done some work on that. The good thing for us is that our proofs of optimality for these algorithms only require the fact that the summands in the entropy function are concave. So for min entropy, our maximization algorithm still applies. And it would be interesting if somebody were to look at other entropies and even G leakage, which is a different measure, and see whether the algorithms work as they are, which for some of them they do, or what modifications need to be made.
Okay, thanks.
Thank you.
Anybody else have questions? Yeah, one more.
Sorry, I have another quick one. So what is the assumption on the approximate model counting? You said that you need to buy, I guess the bounds need to be sound?
Yes. The bounds need to be sound in that we make the assumption that the bounds are sound, and they are probabilistically sound. So with the threshold that you said at the beginning, 99% probability they are sound. It would be interesting to see if we can do some work where we don't do it probabilistically, but that requires some advancement in the model counting space.
Yeah. Okay, thanks.
Other questions? I have a basic one.
Of course.
When you show the symbolic execution, the often question is, what do you do with loops? So here, if you have a while loop, what do I do with it?
Yeah, so this is one of the limitations that comes from symbolic execution, that we basically have to unfold the loops. We have to look at iteration by iteration, especially for the timing channel. I don't know if there's any way around that, because the timing channel is just intrinsically so correlated with how many iterations of a loop you do.
I guess a quick follow-up question. If we do program analysis or verification, I try to find a invariant. In your case, is it possible to identify some invariants you can work with?
Yeah, I don't want to say anything offhand which might be incorrect. I suspect personally that that's going to be difficult, because invariants are more used to prove correctness, but as for the number of iterations, which is really what we're concerned with, I feel that the invariant is probably not the correct thing to be looking at. But again, I might be wrong about this.
Thank you. Last call for questions. All right, thanks, speaker again. So second speaker, please set up.
Thank you.